Hey everybody, this is Professor Ross, and in this video we'll be talking about confidence intervals again, confidence intervals for a single proportion, and two different approaches to finding those confidence intervals. We can use a simulation-based approach, which we will call the 2SD method, and also a theory-based approach. So let's take a look at a few notes here. And I'll highlight that we have a couple of key learning objectives. Whenever we're talking about confidence intervals, we're thinking about the role of variability or error when we're estimating a parameter. A confidence interval helps us estimate where a parameter is. We also want to be thinking about how the confidence intervals can help us distinguish between statistical significance and practical significance. So we have looked at how we can find a confidence interval by creating a big table of values for our parameter. Here we're calling it a proportion pi, and then testing all of those parameters with a hypothesis test and seeing where we reject pi and we say it's not plausible, and where we accept pi and say, okay, that looks plausible. So I've got an example here. What if we had a sample proportion of about 64.5%, 0.645? If we ran our tests with that proportion and we had some low p-values below 0.05, we can reject those. And then the p-values start climbing higher above 0.05. And right here, of course, between 64 and 65% is our p-hat, right in the center of this interval here. And then they start dropping again. And all of these p-values that are higher than 0.05, we say, don't reject those. They seem plausible. But once we drop below 0.05, again, we start saying, nope, reject those. 73, 74, 75, 76% reject those because they're not plausible with the data we have, our statistic of 64.05, or excuse me, 0.645. I want to highlight a couple things. This region here of plausible p-values is centered around our statistic. And that happens all the time whenever we do this, because right around our statistic, of course, those claims would be plausible. I claim that out in the population, it's 65%. Well, yeah, that lines right up with the statistic we saw, very close to 65%. But then as we head out either direction, it's less and less plausible. So that's an important feature to note as well. Another thing to note is that whenever we're working with these null distributions, they turn out to be normally distributed. And there's some really nice features of a normal distribution we can take note of. One, it's symmetric and it's balanced. We have this center value here, right where our statistic is. And then it's symmetric, it's balanced either way. A second is that we go the same distance, 2 standard deviations down, 2 standard deviations, excuse me, that's down, 2 standard deviations up this way, and those 2 standard deviations then capture 95% for us. So that's another nice feature to keep in mind. So we've got the symmetry balanced around our statistic with 2 standard deviations of the null distribution getting 95%. It is really tedious to find confidence intervals the way that we did it in section 3.1 because it just takes a lot of testing to run all those tests. And so we can use some of these common features we've just noticed to give ourselves a little quicker method to find a confidence interval. It's still going to tell us the exact same thing, this interval of values that we believe are plausible for our parameter, but we don't have to do the tedious work of testing each of those all the way through the interval. So some of the common features: the null distribution is often normal. It has that bell-shaped curve and thus symmetric. Our statistic p-hat is at the center of the confidence interval. The ends of the confidence interval are balanced around p-hat, And so there's the same distance we go up and the same distance we go down that we call the margin of error. About 95% of random samples fall within two standard deviations of the mean of the null distribution. And so that's that distance we're going up and down. The margin of error is the two standard deviations. And one last note, the standard deviation of the null distribution is going to be maximized. It'll be at its biggest when our parameter is in the center, 0.5. So if we're trying to find SD of the null distribution, we should try finding it when our claim is that pi is 0.5. And that'll give us the SD we want for our confidence interval. So these things together give us a little approach to calculating a confidence interval with a simulation-based approach. We can calculate the margin of error by finding 2 times SD, and we can use a simulation with pi as 0.5 to find SD, and then double it. We got ourselves a margin of error, and then we add and subtract the margin of error to and from p hat. Let me just jump back here. Essentially what we're saying is use a simulator to find this distance here, and then we just go from here and we just go 1 2, and it'll give us this cutoff point here, and we go 1 2, and it'll give us this cutoff here. So if we find SD, that's what each of these jumps is here, SD SD. We find SD, we double it, it'll tell us how far to go up and how far to go down. Let's try it out. Here's an example. A 2013 Gallup poll found 69% of 1,034 random adults surveyed said that the Affordable Care Act had no effect on their family. So they polled but a little over 1,000 adults, said, hey, the Affordable Care Act, which was fairly new in 2013, has it had some effect on your family? Close to 70% of them said, nope, no effect on us. We'd like to know, okay, so that's for the close to 70% of our sample said no. What's going to be the percent that we believe this to be true out there amongst all adults in the US? That's what the confidence interval can tell us. Let's find it by calculating a margin of error and then a 95% confidence interval. How can we do that? We need to calculate a margin of error. I'll just call it M, and we can approximate M with 2 times SD, and that means we need to find SD, the standard deviation of the null distribution. So the way we can do that with a simulation-based approach is to simulate the null distribution and then find the standard deviation of it. So the way we want to do this is we want to leave the probability of heads as 0.5. Right now we don't know what pi is. That's what we're trying to estimate. And 0.5 for our simulator gives us the most conservative standard deviation of the null distribution. So we're just going to leave that as that. What's the number of tosses? That should match that 1,034 adults that we had in our sample. And then I'm going to go ahead and crank out 10,000 repetitions. I'm starting to get bigger numbers here. This is, over 1,000 in our sample. I got quite a bit to simulate, but I think it'll handle it okay. Let's take a look. Yeah, it didn't show me any of the little spinny wheels there, but I do get a null distribution here. And now everything I've been looking at is dealing with proportions, and we'll find that when we want to do any theory-based approach, we need to deal with proportions. So I just automatically switch to proportions here. And I can see that I've got my relatively normal distribution here. And the key thing I want is to know how spread out it is. What's the standard deviation? And here we go. SD is 0.016. So that's what I needed, the SD. So what I can do then is center this on my my p hat, my statistic, and I can go 2 SDs up and 2 SDs down. So 0.016 is what I needed from that. Let's go ahead and jot that down. Margin of error is 2 times SD, and so it's going to be 2 times 0.016. And that turns out to be what, 0.032. And now what do I do with my margin of error? I'm just going to kind of visualize this. I've got my 69% in the middle here, 0.69, and I'm going to go up 2 SDs, so 0.032 up, and I'm going to go down 2 SDs, so down 0.032, and that'll give me the endpoints of my confidence interval. So my confidence interval, and this will be a 95% CI. Whenever I do a 2SD, that's always the 95% confidence interval, is 0.69 minus 0.032. And that's going to be the low end. And then the upper end, 0.69 plus 0.032. And a lot of times for confidence intervals, we use this notation. We use parentheses and a comma, and we put our low end number here. That's going to be 0.658. And we put our upper end number here. That's going to be 0.722. So there it is, our 95% confidence interval. What is this telling us? Well, in our sample, we know that 69% said no effect of the Affordable Care Act. Out in the whole population, we believe somewhere between 65.8 and 72.2% of adults would say no effect from the ACA. And so it helps us understand what's going on out there in the population. We feel 95% confident our parameter falls between those two numbers. Okay, so that's a 2SD approach, the simulation-based approach for finding a confidence interval. Let's talk about how to do a theory-based approach. I'm going to talk through the formulas here and talk a little bit about what's going on here, and we'll try it out by hand. But one of the main things to know is if you're doing a theory-based approach, you can always use the theory-based applet, and that'll help you find it pretty easily. So one key thing, though, we have to meet the requirements to use the central limit theorem. The requirements are, once again, the same as what we saw when we talked the theory-based approach with a single proportion. We need at least 10 successes and 10 failures in our sample in order to use the central limit theorem. What does the central limit theorem do for us? Well, it gives us a formula that says, hey, you don't have to use a simulator to find SD. You can use a formula. And it says essentially that things will turn out just like we expect, and you can calculate SD from the formula instead of running the simulation. We have a small problem, though. Our formula involves pi, the parameter, and here we're looking for plausible pi's. We don't have pi. When we do a significance test, we have an assumed pi from the null hypothesis. But here we don't have that. We're trying to figure out what pi is like. So we do a substitution and we use p hat in its place. So p hat, we hope that p hat is something like pi. And for example, the Affordable Care Act example, we hope that that 69% from the sample is something like what we'd see out there in the whole population. So we use that and plug that in, but technically we're not finding SD anymore. We're finding what's called the standard error, but it functions the same way. It's an estimate of the standard deviation of the null distribution. And it uses p hat instead of pi, and we already have p hat, and we know n, our sample size, and we can use that. For a 95% confidence interval, we do, instead of 2SD, we do 2 times SE, this 2 times the standard error, because standard error is taking the place of standard deviation there for us. But otherwise, it works the same. We do 2 SE, we call that the margin of error, we add it and subtract it to p hat, and that's how we get our confidence interval. Another advantage of the theory-based approach is that we don't have to stick with 2. 2 is a good estimate for a 95% confidence interval, but we can also change that number 2 to some other numbers to get ourselves our 90% confidence interval, which is going to be narrower because we have a lower confidence. Or we can change it to get ourselves a 99% confidence level. It's going to be wider, but we get a higher level of confidence. So we can just change the multiplier in the formula from 2 to one of these numbers. You'll notice that the 95% is really close to 2. We just use 2 as an estimate. You can always use 1.96 if you want. So in the end, the formula looks like this. This part here is what we call the margin of error. I was just labeling it as M before. Our multiplier, like 2, or if we use one of these other numbers, times, and then our formula that estimates SD for us, it gives us SE. So 2 times SE. And then our statistic plus or minus that margin of error gives us a confidence interval. So this is the general formula. And as I said, we won't use it a lot, but let's try one with the formula here to see how it works. And then we'll take a look at how we can find it in the applet. So we got the same example. 2013 Gallup poll. Let's say this time we want to calculate the margin of error in a 99% confidence interval, and let's use the theory-based approach. So I'm going to go ahead and fill in the parts of this formula that I know here. P hat, that's our 69%. I'm going to write it as 0.69. One thing to note, in these formulas, it always expects us to use a decimal. So instead of a percent or a fraction. Well, I mean, technically, I guess you could do a fraction, but I always put decimal form in there and not a percent form. And then plus or minus, and now I need my multiplier. And don't forget, for a 99% confidence interval, we have a slightly different multiplier, 2.576. 2.576 times the square root of p hat. Once again, that's our statistic from our sample, 0.69 times 1 minus p hat, 1 minus 0.69, all divided by n, the sample size, 1034. I'm going to encourage you to take a moment and see if you can use a calculator to calculate this value here, and then we'll multiply it by that 2.567. So this is where you want to start. Be careful with that square root. When you punch it in, you want to make sure you do the square root of that entire expression underneath. Okay, so hopefully you're getting something like this. You could round a slightly different, but 0.01438. Now I'm going to go ahead and multiply by the 2.576, and my margin of error here is 0.037. I'm going to go ahead and round to that. So you can see this is actually really close to what we got with the simulation-based approach. When we have a large sample like this with plenty of successes and plenty of failures, they should lead us to pretty much the same result. Once again, how do I get the confidence interval from this? My 99% CI. I'm going to have a lower and an upper. And the lower is going to be 0.69 minus the 0.037. So that's going to be 0.653. And the upper is going to be 0.69 plus the 0.037. So that's going to be 0.727. And there's our 99% confidence interval. What is this? This is saying we feel really confident, 99% confident, that the true proportion of families that would say no, they haven't been affected out there amongst the whole United States, somewhere between 65 and 70, almost 73%. So our true parameter pi falls somewhere in there, and we feel very confident of that. How does it compare to the 95% confidence interval? It is a little bit wider. This is a little lower. This is a little bit higher and a little bit wider because we're getting that trade-off with the higher confidence level. Last, let's take a quick look and see how we don't really have to calculate this by hand most of the time. Punching in an applet is pretty straightforward. So I'm going to take us to the theory-based inference applet to check that out. Um, I want to discard there. And theory-based inference applet. One thing to make sure that whenever you're using the theory-based inference applet, you pick the right scenario. Do we want to have just one proportion? Yes, we're just looking at a single proportion. My n was the sample size, 1034. And I can either use my count or my sample p hat. And I know my p hat was 69%. So I'm going to go ahead and do that. And then all I got to do is check on the confidence interval box, and there we go. We got it. Um, and that's slightly different than what we saw with the 2SD method with the simulator, but pretty close. If I change this to 99, it should get pretty close to what we just saw. Pretty much the same as what we just calculated by hand with a little bit of rounding difference there. So that's it. You just have to put in your n and your statistic, check the confidence interval box, and you can get confidence levels, and you can change that level to 90, 95, 99, whatever you need. So pretty easy with the applet. So that's how we can calculate confidence intervals a lot easier than going through and testing all the different hypotheses. Um, we can use technology to get ourselves a good uh, calculation of those confidence intervals fairly quickly.